Hello everyone. So in this class, we are going to continue our discussion of divide and conquer algorithms. And in particular, we're going to look at our first major divide and conquer algorithm, which is the merge sort algo. Okay. This is part of the course, part of the syllabus, and it's one of the most famous divide and conquer algorithms. So let's begin with merge sort. And as I will explain it, you will also see that all those major steps of divide and conquer, the two major steps that you divide one problem into sub problems and then you combine their results in a clever way. These major steps are uh, there in merge sort. So we will see this. So let me first just go back to divide and conquer and explain to you the motivation behind merge sort and how that motivation is then used to actually make the algorithm. So, as you recall, um, divide and conquer is that I take a problem and I divide it into sub-problems. And then my goal is that while combining the solution of these sub-problems, I will save some time. So the first question that merge sort asks itself is that if I look at the sorting problem, okay, is it possible that I can divide the sorting problem into smaller sorting problems? And then if I can do that, then how much time will it take me to combine the solutions of those sorting problems? Okay. Um, Now, when I'm sorting, basically I have a collection that I want to sort. Well, let's say I have an array that I want to sort. And this array can be divided just like usually in a divide and conquer algorithm, we divide from the center. Okay. So, by the way, today I will also mention that why is it that we are usually so far dividing problems into two equal chunks, dividing them into two parts rather than, let's say, three or four or so on. So, I will come back to that. But in order to divide a sorting problem, we can just divide the array into two halves. Like in the fast power algorithm, we divided the power into two halves. So we can divide the array into two halves. And let's, for the time being, assume, okay, that the two halves can be sorted. So जो दो child problems हैं, let's say कि वो sort हो जाती हैं somehow. We'll come back to okay, how they will be sorted. But this assumption that they are somehow sorted will help us for now thinking about the combine phase. That if two sub arrays, meaning let's say the two halves, if they are separately sorted, and then if I want to combine their solutions, can that be done efficiently or not? Because that is the most important thing. Divide and conquer तभी possible है कि अगर आप जो सॉल्यूशंस हैं आपकी प्रॉब्लम्स के उनको क्लेवरली और एफिशिएंटली कंबाइन कर सकें तो ये जो प्रॉब्लम है इसको मैं एक मुख्तलिफ तरीके से स्टेट करता हूँ लेट्स थिंक ऑफ एन एक्सपेरिमेंट in our mind. If I give you a pile of pages, okay, so there is a tall pile of pages and it contains, maybe 100 pages, and they are all shuffled, meaning her page के ऊपर एक number है, but they are obviously not in order. And our goal is to put them in order. So that is the traditional sorting problem that you have 100 pages. In this case, maybe you can have n pages and you want to sort them all. Okay. Meaning you want to bring the smallest number page right at the top and then number two page and number three page and so on and so forth. So this is the usual sorting problem. And you have seen obviously some quadratic time algorithms. In particular, you have seen bubble sort or selection sort. They take n square time. And that time comes from the fact that there are roundabout n square pairs of numbers. And when I make all the comparisons, तकरीबन n square time lag jata hai. So that is the sorting problem. Now let me change that problem. Let me say, think of a different problem. Okay, forget about the sorting problem for now. So let's change the problem. Let's say I have two piles of 50 pages each, and both of these piles are separately sorted. So the first pile of pages is sorted, okay, and the second pile of pages is sorted. So these pages are not necessarily, I'm not saying that these, like, one pile contains pages from 1 to 50 and the other from 51 to 100. It's not like that at all. There is a very random division of pages. So some 50 pages go to the first pile and some 50 pages go to the second pile, but both piles are separately sorted. Okay. So now the problem is the following. I want to put them both together, or let's say merge them both together. So we use the word merge for it. Merge them both together into a single sorted pile. Okay. So that is exactly the combine phase. If an algorithm can divide itself, like divide the problem into two subproblems and solve them separately, sort them separately, then the problem would be to put them back together. तो उसमें कितना टाइम लगेगा? So ये प्रॉब्लम अब सॉर्टिंग की प्रॉब्लम नहीं है, ये मर्जिंग की प्रॉब्लम है. और अगर रियल लाइफ में आप जरा इस थॉट एक्सपेरिमेंट को इसमें अपनी लॉजिकल कंक्लूजन पे लेके जाएं कि आपके पास दो पाइल्स हैं, दोनों सेपरेट में सॉर्टेड हैं. हाउ विल यू put them together into a single sorted pile? So you should pause the video for a minute, think about how you will do that, and then continue watching. So I hope that most of you have been able to work this out. You have two piles of pages. आप दोनों piles को अलग अलग से देखेंगे. Let's say जो पहली pile है उसके top पे पड़ा हुआ है page number 1, और दूसरी जो pile है उसके top पे पड़ा हुआ है page number 6. So obviously, which one will you pick up first? Obviously, you will pick up page number 1 first, because that will become the first page of the overall sorted array. Okay. And then you see that the second page in this pile jahan se aapne number 1 uthaya, that is 2. So again you compare 2 and 6 which is in the other pile, and again the smaller one moves to the overall sorted array, and this process continues. So you look at the top of the two piles and you pick the one page which is smaller, and that page becomes the next page of the overall sorted array. Okay. And this process continues until one of the piles at least is empty, and then the rest of the pile, you can just put that pile at the end of the overall sorted array, and the entire uh, you know the two piles would be merged into a single sorted pile. So you can just go back and listen to this entire process again if you have any doubts about it. But let me explain this now in terms of arrays and numbers rather than paper and pile. So let's look at this picture right in front of you. There are two arrays here, and these two arrays, well, they are not of the same size. One has 5 elements, the other has 4 elements. In merge sort, we will see that both these problems will be, both the sub problems, sub arrays will be of equal size, or they will at most differ by 1. So in this case, you have these two sub arrays, and if you look at it, both of them are separately sorted. This one is, you know, L for left and R for right. This one is sorted in itself, and this one is sorted in itself. And what we want is to put these two together in a single array, which is overall sorted. So this third array, let's obviously this array, the third array where you are doing the merging, should have 9 slots in it, because overall there are 9 elements and you need the 9 slots. Also in the merge sort algorithm, this third array, it may not be a single array of size 9. Okay, I mean, this place where you are sorting, it may actually be a part of a bigger array. Okay, so मैं ये 3 dots लगा रहा हूँ. कि ये जो एरिया है, इस केस में 9 एलिमेंट्स का एरिया, this may not be a single array of like a standalone array of 9 or any size. It may be a part of a bigger array also. You just have to have an area of 9 slots. And these 9 slots are right here. Okay. Let me just draw these. So there are 3, 4, 5, 6, 7, 8, and 9. Okay. So what happens? So जिस तरह pile और paper piles के example में था, you are always looking at the top of the two piles. So यहाँ पर भी ये जो दो arrays हैं, I will always be looking at the next element in both of these two arrays. So here I will have to keep a pointer so at the start I will have to keep a pointer index at the beginning of the two arrays. Okay, so I keep these indices at the beginning of the two arrays. And the the comparison that I will be making is the following. So this is the comparison, and it will be done in a loop, obviously, because there will be many comparisons like this, like at least 9, I think, 9 or something like that. So in fact, slightly less than 9, we'll see. So kya hai? I will maintain an index in L. That index is I. So this pointer here, this should be I. And then there is an index in R, which is J. So I is basically the top of this pile, and J is the top of this pile R. And we compare the ith element of L with the jth element of R. Okay. And whichever is smaller, it moves into A. And A के अंदर indexing करने के लिए will keep some number K. So K will be currently right here at the beginning. So if we look at this example, Li, which is 2, and Rj, which is -6. So definitely Rj is smaller. So this is the one that will move. Okay, so जो चीज़ यहाँ move होगी वो ये -6 है. Okay, और -6 जब यहाँ move होगा तो जो आपका ये pointer है, जो आपकी index है j, it's going to move forward, right? That is going to move here. Uh, and now this is j, right? So j is actually at this 0. So this is the top of this pile. And then the top of this pile is just the same as last time. So it is, I is here. And again, another comparison, and again, 0 will move here, right? J पे जो number है, that was smaller. So this will move here. K move करके यहाँ पर अब second index पे आ गया, जो भी index है. और यहाँ पर आप का जो J है वो भी मजीद आगे move होकर इधर आ गया. So now the comparison, Li, I is still 1, so Li is 2, and Rj is 5. So now this is the comparison. And now this time we will pick up the element from this pile, and that's 2. So 2 comes here, right? 2 comes here. And this time J will not move, but I will move, right? And I will come to this slot. So which is the next number to be moved? 4, which is smaller, comes here, right? And I moves forward. So I moves and it comes to 6. Next comparison, 5 will move. So 5 comes here, right? 5 will be copied, I should say. And J will move. So J will go to the last slot. And now after this 17 is just bigger than everything in this array. But obviously we will find it out one comparison at a time. So 6 compare होगा 17 के साथ, 6 is smaller, so ये यहाँ copy हो जाएगा. And obviously जब ये copy हो रहा है तो ये I आगे move कर रहा है. So look at this piece of code, the way indices should move. K is always going to move because something is copied here. But every time either I moves or J moves, right? Depending upon copy कहाँ से हो रही है. So 6 move हुआ, तो 6 कॉपी हुआ तो आई आगे मूव कर जाएगा, आई चला जाएगा 8 पे, वो भी छोटा है 17 से, सो 8 भी यहाँ आ जाएगा, और इवन 11 छोटा है 17 से, तो यहाँ पे 11 कॉपी हो गया, के यहाँ तक पहुँच गया, और आई जो है वो अब एक्सीड कर गया है. So actually we will stop copying. Actually we will stop not copying but stop comparing, because now we know that whatever is left in R is bigger. And imagine that R had many elements here, maybe 18, 20, 26, etc. All of them are bigger than the biggest thing in L. So all of them will just be copied here now. And remember, they are already sorted because everything in R is already sorted. And also similarly we could have had a situation जहाँ पर L में जो लास्ट एलिमेंट है या कोई एक एलिमेंट है जो बहुत बड़ा था और R पहले खत्म हो जाए, तो if one of the piles ends before the other one, you just take the remaining pile and without any comparisons just copy it here. So इस case में the remaining pile is this 17 only, so that is just copied here. Okay, but if it was more than one elements, they will all be just copied here. 17, 18, 26, whatever, they will be copied. So at the end of the day, the entire thing here has been shifted or copied here. So two separate problems, sub-problems, which were already sorted, their outputs have been combined into a single sorted array. And I hope that all of you can um, guess that if the total number of elements was n, then this entire process just takes O of n time. Okay, this is not difficult to see. There are a total of n elements. I'm passing through all these elements. So I'm just touching every element once. Okay, so there's O of n number of iterations, right? And in each iteration, I'm just making this kind of a comparison. And this is all O of 1, as you can see. Even after the comparisons stop, I have some elements remaining either in L or R, which will be just copied here. Okay, so वो अगर k elements बच गए, sorry, let's say अगर अगर कोई w elements बच गए हैं, so we will just copy those w here. So exactly n things are copied into this array, and no more than n comparisons have been made. So overall, this is just O of n. So this is where merge sort gets its inspiration. Merge sort now knows that if somehow we just divide the problem properly into two sub-problems, and if those two sub-problems are separately sorted, then combining them does not take O of n square time. Like one array, if we are trying to sort one array, we know bubble sort is going to take n square time. We know that selection sort is going to take n square time. But it turns out that if I have two separately sorted arrays, total number of elements n, then combining them will only take O of n time. Okay, so this will give us the motivation for merge sort, that divide the original problem into sub-problems and try to sort everything by not sorting, but by merging, okay, by combining, which is just going to be possible in O of n. So now in the next video, we're going to see how this merging procedure can be used to do merge sort.